Hello, linear algebra students. Today's video lesson is on the LU factorization of a matrix. Now, a square matrix is upper triangular if all of its entries below the main diagonal are zeros. Give some examples below. So let's do a 3 by 3 matrix. The main diagonal can be any numbers you want. So I'll just put in A, B, C. Doesn't matter what they are. Below the main diagonal has to be all zeros. And so we do need a 0 in the 2-1 position, the 3-1 position, and in the 3-2 position. And the other entries can be whatever they want as well. So let's go ahead and just put D, E, F. So basically any 3 by 3 matrix of this form, where A, B, C, D, E, and F can be any number, is going to be called upper triangular. So keep in mind that here's an example of an upper triangular matrix. I'll put 1, 2, 3 on the main diagonal. Make sure there's zeros below the main diagonal. And then if I were to also put zeros above the main diagonal, then this would also be called an upper triangular matrix. Notice it is also a diagonal matrix in this case. However, as soon as I change one of the zeros above to something else, such as a 7, then this is no longer a diagonal matrix, but it is still an upper triangular matrix. Now, a lower triangular matrix is similar, except that the zeros must be above the main diagonal. And so I'll give a 3 by 3 example of this. Again, you can have A, B, C, anything you want on the main diagonal, as long as above the main diagonal, these entries here, so the 1, 2, 1, 3, and 2, 3 positions all have to be 0. And then the other entries can be whatever they want as well. And this would be called a lower triangular. Now for a 2 by 2 matrix, let's say we have a 5 and a 1. We need a 0 in the 1, 2 position, and then in the 2, 1 position could be anything it wants. If it's like an 8, then this is a lower triangular matrix. If the 2, 1 position is also a 0, then we still say this is a lower triangular matrix, but it is also a diagonal matrix. Now you can imagine what these matrices might look like if they were larger dimensions, such as 4 by 4, 5 by 5, etc. Now a triangular matrix is just a matrix that is either upper or lower. Now the question that is on the table is, does a triangular matrix have to be square? Well, a lot of definitions in textbooks and by mathematicians insist that to be called an upper triangular or lower triangular or just a triangular matrix, that it must be a square matrix. But we're going to use the word upper and lower triangular a little bit loosely. For example, if we were to have a 2 by 3 matrix, let's put some entries in here. 1, 2, 3. I'm going to put a 0 right here, and then 4, 5. Some people do still consider that the 1, 4 constitutes the main diagonal, and the entries below this main diagonal is a 0. So we will move forward considering this to be an upper triangular matrix as well, because it does have zeros below the main diagonal. Next page. Complete the statements below where U is an upper triangular matrix, L is a lower triangular matrix, and T is just any triangular matrix, could be upper or lower. Give a few examples to illustrate each. So we have an upper triangular matrix times another upper triangular matrix. I'm going to give examples that are 2 by 2, but these examples will generalize to higher dimensions. So if we were to have an upper triangular matrix, let's go with a 1, 2 on the main diagonal. And to be upper triangular, it means the zeros are below the main diagonal. And let's put a 3 up in that other position. Let's multiply it by another upper triangular matrix, 4, 5, 6, and a 0 in the 2, 1 position. So here's a product of two different upper triangular matrices. Let's go ahead and multiply them and see what we get. I'll do this multiplication quickly in my head. We get 4 plus 0, so we get 4. Then we get 0 plus 0, so 0. Then we get 5 plus 18, which is 23. And we'll get a 0 plus 12. I want you to observe something, that when you have an upper triangular matrix, you multiply it by another upper triangular matrix, you get an upper triangular matrix again. So we'll say that the result over here is some U3. This is simply trying to say that an upper times an upper will still be an upper. I'll leave it you to verify with some examples that a lower times a lower will still be a lower. So we'll go ahead and just write L3 here. If you take an upper triangular matrix and do its transpose, you can probably guess what's going to happen. Let's call this matrix right here our U, and go ahead and just do U transpose. So U transpose is you take the first row of U and make it a column instead, so it becomes 1, 3. And then the second row of U is 0, 2, and that becomes the next column. You can see that reversed where the zeros are. Instead of the zeros being in the lower left corner, they're now in the upper right corner, producing therefore a lower triangular matrix. So we'll say that the transpose of an upper will produce a lower. Similarly, the transpose of a lower will produce an upper. Now, the determinant of a triangular matrix, so T, remember, is just any old triangular, so this could be upper or lower. Let's go ahead and do an example of a 3 by 3, and I'll do an example that's upper triangular. Let's go ahead and put the main diagonal to be 1, 2, 3. This is going to be upper triangular, so I'm going to put zeros below the main diagonal. And let's go ahead and throw in some other numbers up here, 4, 5, 6. Now the question we want to ask is, how do we calculate the determinant of this? Since this is a 3 by 3, I could use the technique of repeating the first two columns, augmenting this with the first two columns, and then multiplying the diagonal entries, these diagonal entries, these ones, and keeping the sign, and then doing the reverse diagonals and changing their signs. But I want you to notice something, that of all of these products, all of them involve a zero because of the triangular nature of this matrix, except for the very first product, the 1, 2, 3. This is the only product that is not guaranteed to have a zero involved. So in this case here, it's just 1 times 2 times 3, and we get 6 is the determinant. Another way to consider the determinant of a triangular matrix is to imagine all of the possible elementary products. An elementary product, if you recall, is a product of 3 entries of this matrix, and this is a 3 by 3, so there's 3 factorial, there's 6 of them. Well, one elementary product that's possible is the product of the main diagonal. This product is going to give me 6. Another possibility of an elementary product is these 3 entries, but notice that does forcibly involve a 0 because this is upper triangular, so this elementary product will be 0. And these are the only 2 elementary products that involved the 1, 1 position. Every other elementary product is going to involve either this 0 or this 0. Therefore, all the elementary products except for the main diagonal will be 0. So basically, the determinant of a triangular matrix is still just the product of the main diagonal. So we'll say the product of the t sub ii's. So just multiply the t11, the t22, the t33, etc., depending on how large the matrix is. Multiply all the entries on the main diagonal, and that's how you get the determinant of a triangular matrix. Of course, if one of the entries on the main diagonal, at least one of them, of course, if at least one entry on the main diagonal is 0, then we'll have a determinant of 0. But if all of the entries on the main diagonal are non-zero, then the determinant of the triangular matrix will be also non-zero. Now let's consider the inverse of an upper triangular matrix. Let's go ahead and consider the 3 by 3 that I have written already. And I'm going to augment this 3 by 3 matrix by putting the 3 by 3 identity matrix next to it. And our goal is to do row operations until the matrix on the left is the identity. Well, notice that I do need to potentially change the main diagonals to 1. And we can do that pretty easily by doing 1/2 of row 2 and 1/3 of row 3. That will get 1s on the main diagonal, both here and here. But once you have those 1s in those positions, you just need to do the third row operation to make zeros up above. For example, let's just go ahead and do 1/2 of the middle row, which will give me 0, 1, 3, 0, 1/2, 0. And then I'm going to do the row operation of doing -4 times row 2 and adding it upwards to row 1 to make this entry here a 0. So as I attempt to do this, I only need to change the entries above the main diagonal to 0, so these 3 entries. So I'm only going to need to do the third row operation by adding a multiple of one row to a row above it to change that row that's above it. And so this will have the effect of not impacting these 3 entries down here. They will stay 0. So by the time I'm done with this, the inverse matrix will still be an upper triangular matrix. So the inverse of an upper triangular matrix will be yet another upper triangular matrix, but won't necessarily be the same. So I'm going to put a subscript on this one just to differentiate it from just plain old U. But what this is trying to communicate is that the inverse of an upper is still an upper. Similarly, the inverse of a lower triangular matrix will still be a lower triangular matrix, but not necessarily the same one, so we'll put a L sub 1 there. Okay, let's go to the next slide. Some matrices that are m by n, so notice that's non-square, can be factored into the product L times U, where L is an m by m lower triangular matrix, notice it's L is square, with 1s on the main diagonal. So that's a special kind of lower triangular matrix, insisting that we have 1s on the main diagonal. And U is an m by n upper triangular matrix. Now notice U is not square, but we're still calling it an upper triangular matrix, and we talked about that a couple slides ago. If possible, find the LU factorization of the matrices below. When successful, calculate the determinant of the given matrix if possible. Okay, let's focus on this first one. The goal here is to express this matrix as the product of a lower square triangular matrix and an upper, potentially non-square triangular matrix. Now, this matrix we're focusing on is a 2 by 2, so L would also have to be a 2 by 2 matrix, and that's going to force U to also be 2 by 2, so that the end result is 2 by 2. And L is a lower triangular matrix with 1s on the main diagonal. So that means there's a 0 in the 1, 2 position, but we don't know what's in the 2, 1 position. So I'm going to just put a letter A there for now. And U is an upper triangular matrix with not necessarily 1s on the main diagonal. So I don't know what the main diagonal is currently, so I'll put a B and a C. But it's upper triangular, so the 2, 1 position is 0, but the 1, 2 position is unknown. So I'm actually going to put the C here and the D there. It doesn't really matter. We have 4 unknowns here. The A, the B, the C, and the D are unknowns, and we need to figure out what they are. We're going to do this just by investigation. We're going to go ahead and multiply these two matrices together and then determine what A, B, C, and D have to be so that the result matches the original matrix. So doing matrix multiplication, B times 1 plus 0 times 0, so we just get B in the 1, 1 position. Then A times B plus 1 times 0 will just be AB in the 2, 1 position. And continuing with our multiplication, we have C times 1 plus 0 times D. That's just going to be C. Then we have C times A plus 1 times D. So we have AC plus D. Now we want this result to match the original. So B has to be equal to 2. C has to be equal to 1. A times B has to be minus 4. And AC plus D has to be equal to 0. So this creates a system of equations that's rather easy to solve, right? We had B right away has to be 2. C right away has to be 1. And we have A times B has to be negative 4. And we know that B is 2, therefore A has to be negative 2. And then finally we have AC plus D has to be 0. And we know A and we know C. A times C is going to be negative 2. Therefore D has to be positive 2. And just like that, we've created what's called an LU factorization. So let's go ahead and write down summarize what these two matrices actually are. L and U. L has 1s on the main diagonal, and A was in the 2, 1 position, and A has to be negative 2. And then a 0 up there. U is upper triangular, so the 2, 1 position is 0. And the main diagonal is B and D. B was 2, D was 2. And then the C position, which is the 1, 2 position, was 1. Now, I leave it to you to verify that when you multiply these two matrices together, that you do, in fact, get the original matrix that we started with. All right, the next one. So again, we have a 2 by 2. So we'll do the exact same setup we did before. So I'll be able to copy and paste. But this time we have that the B has to match this 0. The C has to match this 1. The AB has to match negative 3. And then the AC plus D has to match 0. So this gives me that B has to be 0. C has to be 1. But notice right here, we have a problem with the AB. If A times B has to be negative 3 and B has to be 0, then AB can never be negative 3. So this is a not possible. So this is an example of a matrix that just does not have an LU factorization. All right, let's go to the next one. Here we have a 2 by 3. So if this does factor into an L times U, the L will have to be 2 by 2, but the U will have to be 2 by 3. In order for this matrix multiplication to make sense. Now the L's is going to still have 1s on the main diagonal and an unknown 2, 1 position, but a 0 in the 1, 2 position. And then the upper triangular matrix is non-square in this case, but it's going to have an unknown first row, so we'll say a B, C, D. It must have a 0 in the 2, 1 position, but the other two entries are also unknown. They could be anything. We got to figure out what they are. I'll go ahead and do the matrix multiplication. I will go ahead and do this quickly again. We were going to have B plus 0, B, then we have AB, so there's our first column. Second column would be C plus 0, so just C, and then AC plus E. And then the third column would be D plus 0, so just D, and then AD plus F. There we go. Now equating the entries, just to do the first row, that's the easy one. So B has to be 2, C has to be 4, and D has to be 1. Now we have that a times b has to be 1, and b is 2. Therefore, a has to be 1/2. Then we have ac plus e has to be 2. And we know a is 1/2. We know c is 4. So 1/2 times 4 is 2. Therefore, 2 plus e has to be 2. Therefore, e has to be 0. And then finally, we have AD plus F has to be -2. Well, A is 1/2, and D is 1. So 1 times 1/2, I'll go ahead and do this as an extra step. So we have a 1/2 right there, plus F has to be -2. Subtract 1/2 from -2, and we get F has to be -5/2. Therefore, we now have an LU factorization. The L in this case is our 2 by 2 with 1s on the main diagonal, a 0 in the 1, 2 position, and in the 2, 1 position was A, which is 1/2. And our upper triangular matrix is BCD, where B was 2, C was 4, D was 1. And then 0, EF, where E is also 0, and F is -5/2. Now I leave it to you to verify that when you multiply L times U, that you will get the original matrix. And now let's do our 3 by 3. If in fact this does has an LU factorization, it will factor into L will be 3 by 3, and U will also be 3 by 3. L will have to have 1s on the main diagonal, 0s above the main diagonal, and then the other 3 entries are yet to be determined. So we're going to say A, B, C. And then the upper triangular matrix will have D, E, F, G, H, and then I with 0s below the main diagonal. Remember, the main diagonal of the upper don't necessarily need to be 1. That's only the case for the lower. Now when I multiply these two, we're going to get, the first column will be D, then AD, then BD. The second column will be E, and then AE plus G, and then BE plus CG. The third column will be F, and then AF plus H, and then BF plus CH plus I. Now we're going to equate entry by entry. So this gives us that D has to be 1, E has to be 2, F has to be 0, A times D has to be 1, and since D was 1, we know that A also has to be 1. AE plus G has to be 3. Well, A is 1, E is 2, so A times E is also 2, therefore G has to be 1. And then we have AF plus H has to be 2. Well, F is 0, so we get really H has to be 2. Now looking at the third row, we have BD has to be equal to 2, but D is 1, therefore B has to be 2. Then we have BE plus CG, that has to be equal to 3. B is 2, E is also 2, so we get 4, and G is 1, so basically we have 4 plus C has to be 3, therefore C has to be -1. And then the final entry, we have BF plus CH plus I, that has to be equal to 4. And B is 2, F is 0, so that first term goes away. C is -1, H is 2, so we get a -2 plus I has to be 4. Add the 2 over, therefore I has to be 6. And we have an LU factorization. L will be 1s on the main diagonal, 0s above the main diagonal, and then A was 1, B was 2, and C had to be -1. And our upper triangular matrix, also a 3 by 3. D was 1, E was 2, F was 0. Then we had a 0 in the 2, 1 position. G is 1, H is 2, and then a 0 and a 0 again, and then the final entry was I, which is 6. And then I leave it to you to verify that when you multiply L times U, you will get the original matrix. Okay, the last sentence in our instructions says that when successful, calculate the determinant of the given matrix, if possible. So that means when successful, finding an LU factorization. So in this first case, we were successful in finding an LU factorization, and we want to calculate the determinant of this matrix. Well, we have A is equal to LU. Therefore, the determinant of A will equal the determinant of LU, and we can use a property of determinants that we can do the determinant of L and U separately. And since L and U are both triangular matrices, finding their determinants is as easy as multiplying the entries on their main diagonals. So looking at L, the determinant of L will be 1 times 1, which is 1, where the determinant of U will be 2 times 2, which is 4. And so we get 1 times 4, which is 4. Of course, this is an easy matrix to find the determinant of the original. 2 times 0 minus negative 4 times 1 is also going to confirm that we get 4. Now in case 2, we were not successful in finding an LU factorization, but we could get the determinant of the original matrix, and we would get a positive 3 by just doing our crisscross method. Matrix 3 is not square, so we can't even find its determinant, but now let's look at the last matrix, the fourth matrix here, that's a 3 by 3. And let me move this work up here. The determinant of this 3 by 3 can be found by doing the determinant of L and then times the determinant of U. And since L and U are both triangular matrices, we just need to multiply their main diagonals. So the determinant of L is 1 times 1 times 1. In fact, L is a special triangular matrix in that we designed it to have 1s on the main diagonal. Therefore, the determinant of L should always be 1 when you do an LU factorization, as described. And the determinant of U will be 1 times 1 times 6. So in the end, we get a determinant of 6. So when you're successful in finding an LU factorization of a matrix, it's very easy to get the determinant of that matrix. You really just have to do the determinant of the upper triangular matrix factor. Okay, let's go to the next slide. Identify the row operation associated with each elementary matrix below. All right, for this first one, we have 1s on the main diagonal and then a non-zero entry right here. So this was accomplished by multiplying this one by 3 and adding it to what used to be a 0 right there to get a 3 in that position. And so this is a 3 times row 2, and then add that to row 3 to make a new row 3. So notice it's using a row, it's adding a multiple of one row and adding that to a row that's lower than it to get a new row that's lower. And that has the effect of basically putting a non-zero entry somewhere in this lower corner, so somewhere below the main diagonal, while the main diagonal stays 1s. Over here, something similar, we have a non-zero entry in this position right here. So we use the 1 above it, so we multiply row 1 by negative 5, add that to a row lower than it to produce a new row in that position. And this has the effect of basically putting a non-zero number somewhere in the entries below the main diagonal. Now notice that when you do this kind of row operation, where you replace a row by adding a multiple of a row higher than it to that row, that you produce a special kind of lower triangular matrix that has 1s on the main diagonal and then some non-zero entry below the main diagonal. Now we're going to find their product, and then we'll find the inverse of all 3 of these matrices. Okay, multiplying E1 and E2 together, we'll do this quickly. The first column will be 1 plus 0 plus 0, so just 1. 0 plus negative 5 plus 0, so negative 5. And then 0 plus negative 15 plus 0, so negative 15. The second column will give us 0 plus 0 plus 0, 0 plus 1 plus 0, 0 plus 3 plus 0. And then the final column will be 0 plus 0 plus 0, 0 plus 0 plus 0, and 0 plus 0 plus 1. Notice, as we discussed before, when you multiply 2 lower triangular matrices, you get another lower triangular matrix. Furthermore, notice that the main diagonal is still 1s. Now let's find the inverse of all of these matrices. Well, for E1 and E2, we can use what we know about how to reverse a row operation to determine the inverse. So if you were to do the reverse row operation, which would be negative 3 times row 2 and add it to row 3, create a new row 3, but do that row operation to the identity matrix, and you are going to get the following inverse matrix. It's going to be basically the same as E1, except it's going to have a negative 3 in that position instead of a positive 3. And this is the inverse matrix. Similarly, the inverse matrix of E2 will be just like E2, but it is going to have a positive 5 in the 2, 1 position. Now to find the inverse matrix of their product, we could do this a couple of ways. I could just try to find the inverse of this matrix right here, or I can use the following fact that if you want to find the inverse of a product, we talked about this a few topics ago, that this is going to be the product of the inverses in reverse order. So it should be E2 inverse times E1 inverse. So it'll be E2 inverse, which I'll write in shrink right there, times E1 inverse. So do this matrix multiplication in this order, and this should give us the inverse matrix here. So we're going to get 1 plus 0 plus 0, 5 plus 0 plus 0, 0 plus 0 plus 0, and then 0 plus 0 plus 0, 0 plus 1 plus 0, 0 plus 0 plus negative 3, and then 0 plus 0 plus 0, 0 plus 0 plus 0, and 0 plus 0 plus 1. And this is the inverse of the product. All right, then notice all these inverses are also the special lower triangular matrices still. They have 1s on the main diagonal, and the only non-zero entries would be below the main diagonal. 0s above the main diagonal. Note that if a matrix can be made to be upper triangular using only the row operation of adding a multiple of a row to a lower row to change that lower row, then an LU factorization is possible. Now, in the previous slide, we noticed that not every matrix does have an LU factorization. So this would be a condition that would guarantee we could find an LU factorization. Let me illustrate why this is the case. So suppose we start with some matrix A. We do only row operations where we add a multiple of a row to a lower row to change that lower row, right? That's exactly what these E's are doing up above. You're adding a multiple of one row to a lower row to change that lower row, and it winds up producing these elementary matrices that are these special lower triangular matrices. I say special because they have 1s on the main diagonal. And we know that their products and their inverses are also these special lower triangular matrices. Therefore, if you can take a matrix A and perform such a row operation and then do a whole series of them, and all of these E's I'm writing are only for this special kind of third row operation, and you can produce an upper triangular matrix by doing only this. Okay, so let's just call this product of elementary matrices B, and we know that the product of all of them will still be special lower triangular, and the inverse of B will still be special lower triangular. Therefore, we can say that A is equal to B inverse times U, where specifically B inverse, to invert that product, you do the reverse product of the inverses. So it'll be this product here times U. All of these inverses of these elementary matrices are special lower triangular, and their product is special lower triangular, meaning that we do have something of the form L as described before. So we have L is got 1s on the main diagonal, and then 0s above the main diagonal, and then potentially non-zeros below the main diagonal. But as you can see, we have A's expressed therefore as L times U. All right, this actually opens up a interesting strategy for finding the upper and lower triangular matrices if a matrix has an LU factorization. This method is called the multiplier method. We'll demonstrate it here below. So we start with the matrix A, and we limit ourselves to only doing the third row operation, where I take a multiple of one row and add it to a lower row to change the lower row, to convert A to an upper triangular matrix. We'll keep track of those row operations. In this first case, so I cannot do any sort of row interchanges, so you can't use those. I also want to avoid doing any multiplying a row by a non-zero constant. Let's limit ourselves only to the third row operation and where we work down the matrix. So I want to get a 0 right here. So if I multiply the top row by 2 and add that down to the second row, this is an acceptable and allowed row operation. And this will yield a new matrix. The first row will be the same, 2, 1. And the second row will change. We'll have 2 times 2 is 4, add to negative 4 is 0. 2 times 1 is 2, add to 0 is 2. And just like that, in one row operation, we have an upper triangular matrix. And we're going to stop right here. Well, as we saw above, to convert a matrix A into an upper triangular matrix, we do a series of elementary row operations of this special type. And then to create L, I do that same series of row operations, but I do their inverse operations and in reverse order. And I do that to the identity matrix, and that will create the lower triangular matrix that I'm looking for. So going down here to find the lower triangular matrix, I begin with the identity matrix of the same size. And we only used one row operation to turn A into U, so I just have to do the inverse of that row operation. And the inverse would be, we do -2 times the first row and add it to the second row. And this produces a new matrix. We'll have the top row the same, 1, 0, but the bottom row will become -2, 1. And just like that, we create the lower triangular matrix. Notice that this matrix A is a matrix for which we've already found the LU factorization. We did it a couple slides ago. Let's go back to that. But up here we did a method that's just called a direct examination method, where we set it up, we multiplied, and we determined what the unknowns had to be in order to have an LU factorization. And the LU factorization that we got right here matches the results that we got using this new method. All right, let's focus on the matrix B here. My goal is to turn B into an upper triangular matrix. And I want to limit myself to only doing row operations of the third type. So I want this to be a 0 next. So I'm going to do -1/2 times the first row and add that to the second row. And that should put a 0 in that position. So this will produce the following matrix. The top row will stay the same, 2, 4, 1. The bottom row, -1/2 times 2 is -1, add to 1 is 0. -1/2 times 4 is -2, add to 2 makes a 0. And -1/2 times 1 is -1/2, add to -2 is -5/2. And this is an upper triangular matrix, right? The main diagonal is right here, but what mattered is that we had a 0 in this position. This is not square, so we're being a little bit loose when I call it an upper triangular matrix, but this will be our U matrix in our factorization. Now to find the corresponding lower triangular matrix, I begin with the identity, it has to be square. And this case, we used only one row operation, so we do that same row operation, but it's inverse, which would be do 1/2 times the first row, add it to the second row. And this yields the following. We get a 1, 0, and then a 1/2, 1. And this would be my lower triangular matrix. And you'll notice that these results match what we did 2 slides ago, right here. Again, the method we used on this slide, we'll call that the direct examination method to find the LU. Whereas down here, we're using what's called the multiplier method. All right, now let's look at this C. Using only the third row operation and only affecting rows that are lower, I'm going to go -1 times the first row, add that to the second row. And let's just only do one row operation at a time, just to keep track of the order in which we do them. So this will yield a new matrix. Top row will be the same. Third row will be the same. But we'll have a new middle row, and that's going to be a 0, 1, 2. And now I want to focus on this entry here. I want that to be a 0. So we're going to multiply the top row now by -2 and add that down to the third row. This will yield, top 2 rows will not change, but the third row will change. We'll have a 0 here. We have a -4 plus 3, that's a -1. And then a 0 plus 4 is 4. Now, we're not yet at an upper triangular matrix because we have a non-zero in this position. We need to be upper triangular. We need all the entries below the main diagonal to be 0. So now I'm going to do one more row operation where I multiply the middle row by 1 and add that to the third row to change the third row. So basically just add row 2 to row 3 to change row 3, and this will produce a new matrix. Top 2 rows will not change. Third row will become 0, 0, 6. And this is now upper triangular. This is our U in our LU factorization. Now to create the lower triangular matrix, I begin with the same size identity matrix, and I do the same row operations, but they're inverses and in reverse order. So I'm going to do this row operation, then this one, but do their inverse operations, which really just means change the sign of those 3 numbers you see there. So the first one I'm going to do is -1 times row 2, add to row 3. So the top 2 rows will not change. Bottom row will become 0, -1, 1. Now I'm going to do the inverse of this row operation. So I'm going to do 2 times row 1, right, the opposite number, 2, times the same row though, and add that down to row 3. Add that down to the same row as I did before. And this is the reverse row operation. This yields, this time the top 2 rows will not change once again, but the third row will become a 2, -1, 1. And then finally, I'm going to reverse this row operation right here. So instead of -1, it'll be +1 times row 1, add to row 2. Same two rows are involved, but we just changed that -1 to +1. So basically, just add row 1 to row 2 to make a new row 2. So we get 1, 1, 0, and we have 2, -1, 1. And once we do the same number of row operations, but they're inverses and in reverse order, this winds up producing the lower triangular matrix that I'm after. And once again, you'll notice that this confirms the work that we got a couple slides ago, looking right here. So this gives you a second method for finding an LU factorization of a matrix if it has one. Let's go to the next slide. The LU factorization of a matrix can be used to solve the system AX equals B as shown below. And this will be true even if A is a non-square matrix. So let's say that A does have an LU factorization. Therefore, the system could be written as LU times the variable vector equals the constant vector B. And U times X will wind up producing a vector. Let's call this vector the Y vector. And so I can really solve the L matrix times some vector is equal to the constant vector B. We're going to solve this for Y, which will be easy to do because L is lower triangular. And you're going to see that when you have upper and lower triangular matrices as coefficient matrices, that the systems are rather easy to solve. And then once I know Y, then I'm going to solve the following. Well, we said that Y was equal to the upper matrix times the vector X is equal to Y. So then we solve this system next ultimately for the vector X. This is ultimately what we're after is vector X. I can basically solve a system of equations by solving two systems, but where the coefficient matrices are upper and or lower triangular, which will be a lot easier to solve. Let's demonstrate that for this next system. So we have a coefficient matrix sitting right here. It's 3 by 3 times the variable vector of UVW equals that constant vector -1, 0, 2. Because there's our 3 by 3 coefficient matrix. Notice this is the matrix for which we've already done an LU factorization. So I can just borrow these these results here. We're going to begin by solving Ly equals B. We'll solve it for Y. So that lower triangular matrix is 1, 0, 0, 1, 1, 0, 2, -1, 1. We're going to multiply that by some vector Y, 3 components, y1, y2, y3 in this case, and set it equal to -1, 0, 2. We'll just convert this back into equations. In other words, do this matrix vector multiplication, and you basically get the following set of statements. y1 has to be -1, y1 plus y2 has to be 0, and then 2y1s minus y2 plus y3 has to be 2. We know y1 right away, and then we can do back substitutions to figure out the others. So this tells me that y1, of course, is -1. y2, therefore, is going to have to be +1, so that y1 plus y2 is 0. And if y1 is -1 and y2 is 1, we can plug those into the third equation and solve for y3. So we get -2 minus 1, so -3, add it to the other side, we get y3 has to be 5. Okay, next, we solve ux equals y to find x. So I'll borrow this upper triangular matrix that we already found. So there's u times the vector x. Now the vector x is technically these three variables here. You can say x1, x2, x3, but since they were already specified, our vector x's components are uvw is equal to, and then we set this equal to the y vector that we just found. So -1, 1, 5. And we solve this system. But convert these back into equations, and notice you'll get u plus 2v has to be -1. We get v plus 2w has to be 1, and 6w has to be 5. So we can find w first and then back substitute into the other equations to find the others. So this tells me that w has to be 5/6. So I'm going to double that to 10/6 and remove that from 1. So 6/6 minus 10/6 is -4/6, and that's what v has to be. And -4/6 is -2/3. And the top equation doesn't have a w, but does have a v. So double -2/3 is -4/3, and add 4/3 to -1. So adding 4/3 to -3/3 is going to be 1/3. So u has to be 1/3. And this is the solution to our system. Okay, in this case here, if this is our matrix A, then we've already done a LU factorization for it, so I'll go up here and borrow that work. So here's our lower triangular matrix. We begin by solving that lower triangular matrix. We work with that one first. This times the vector, the y vector, in this case would have to be a 2-component y vector, so y1, y2, set equal to our b vector, 0, 1. So we're going to solve this for y1, y2. And when you multiply across, you see that, oh, y1 has to be 0, and 1/2 of y1 plus y2 has to be 1. Well, if y1 is 0, then y2 has to be 1. So here's my y vector. It's also 0, 1. And now I take my upper triangular matrix, multiply it by my x vector, which has 3 components, right, x, y, z. And this has to be set equal to my y vector. My y vector is also 0, 1, same as my b vector in this case. Now we solve this system. Now this system is 2 equations and 3 variables. There's going to be a free variable at play. So I'm going to go ahead and use an augmented matrix to help resolve this from here. So we have 2, 4, 1, 0, and 0, 0, negative 5 halves, 1. This is an augmented matrix, and I want to put this in reduced row echelon form. So I'm going to do a couple things. I'm going to multiply the top row by 1/2, multiply the bottom row by negative 2/5. That's to get 1s in this position and this position. And that gives me 1, 2, 1/2, 0, 0, 0, 1, negative 2/5. And then this is not yet in reduced row echelon form. I do want this entry here to be 0. I'm going to do negative 1/2 times row 2 and add that back to row 1. And this will give me a new matrix. Bottom row not changed. Top row will be 1, 2, 0. And then let's do negative 2/5 times negative 1/2. That's going to be positive 1/5. And then add that to 0, so we get a 1/5 up here. Now our leading ones are only in these positions. I have a leading 1 here and a leading 1 here. So that's the x and z. So y is free. And then our 2 rows suggest that x plus 2y has to be 1/5, whereas in the bottom row says that z has to be negative 2/5. So solve this equation here for x, and that gives you our answer. So x has to be 1/5 minus 2y. Y is free, and z has to be negative 2/5. And this is our solution set. I want you to be mindful that sometimes a new variable is introduced for the free variables. For example, if y is free, sometimes you might see a solution that says, okay, well, let y be t, let it be a new letter. And once you do that, then you say, okay, well, then x has to be 1/5 minus 2t, because y is t. Y is t. And then z, in this case, z is not free, nor is z dependent on y at all. Z still has to just be negative 2/5. So sometimes this is a way to present your answer by letting the free variables be a new variable. Okay, and this wraps up our lesson on LU factorizations and how they are useful in solving systems.